Circular convolution can be found using linear convolution. Method is divided the result of linear convolution into two parts such that first part has n samples and then n corresponding part in order and write as circular convolution. Here n is number of samples in each signal. Given two signals f of n and h of n, each consisting of n samples, if we zero pad each of the signal with n zeros and carry out circular convolution of order 2n, this will equal to linear convolution of two signals f of n and h of n. The fast Fourier transform is a discrete Fourier transform algorithm which reduces the number of the computations needed to find transform. For n point DFT, number of multiplications equal to capital N by small 2 log n base 2, number of additions equal to n log n base 2. Remember, number of multiplications equal to n by 2 log n base 2, number of additions equal to n log n base 2. ఎన్ని additions ఉండాలంటే n log n base 2. ఎన్ని multiplications ఉండాలంటే n by 2 log n base 2. Very important. The main drawback of continuous Fourier transform is that Fourier transform can be defined only for stable systems, whereas Laplace transform can be defined for both stable and unstable systems. Laplace transform. Laplace transform of a general signal f of t. Bilateral or two-sided Laplace transform f of s equal to integration of minus infinity to infinity f of t e power minus st. Unilateral or one-sided Laplace transform equal to f of s equal to integration of 0 to infinity f of t e power minus st dt. Inverse Laplace transform f of t equal to integration of minus infinity to infinity f of s e power st ds. Relation between Laplace transform and Fourier transform f of sigma plus j omega equal to integration of minus infinity to infinity f of t e power minus sigma t e power minus j omega dt dt equal to e power minus sigma t f of omega, where s equal to sigma plus j omega. At sigma equal to 0, s equal to j omega, the Laplace transform becomes equal to Fourier transform. Our Laplace transform calculated on j omega axis is Fourier transform. Fourier transform is used for signal analysis and Laplace transform is used for designing the system. The region of convergence, the range of values of s for which f of s, that is increased to infinity f of t e power minus sigma t less than infinity, is defined. It's known as ROC. Properties of ROC. ROC does not contain any poles. It is bounded by the poles. ROC of f of s contains strips parallel to imaginary axis, that is j omega axis. If f of t is the finite duration, the absolutely integrable, then the ROC is entire spline. If f of t is a right-sided, and if the line RE of s equal to sigma naught is in the ROC, then all values of s for which RE of s greater than sigma naught will also be in ROC. If f of t is a left-sided signal, and if the line real part of s equal to sigma naught is in the ROC, then all values of s for which real part of s less than sigma naught will also be in ROC. For two-sided signal, ROC is the combination of two regions. For stability, ROC must include imaginary axis, that is j omega axis. Solution of Laplace transform is uniquely one when the ROC is given. Is unique only when the ROC is given. Linearity. A into x1 of s plus b into x2 of s. ROC is R1 intersection of R2. Remember, R1 intersection of R2. Time shifting x of t minus t naught e power minus st naught x of s. That ROC is only capital R. Shifting in s domain e power s naught of t x of s minus s naught. Then ROC is shifted version of R. Time scaling x of a t equal to 1 by modulus of a x of s by a. Scaled ROC. Conjugation x conjugate of t equal to Laplace transform x conjugate of s conjugate. ROC is R. Differentiation in time domain d by dt of x of t equal to s on x of s at least R. Differentiation in s domain minus t x of t dx of s by ds. ROC is R. Convolution x1 of t convolution with x2 of t. Laplace transform x1 of s into x2 of s. ROC is nothing but R1 intersection R2. Remember, convolution means R1 intersection R2. Where is integration of minus infinity to t x of tau d tau equal to 1 by s x of s. R1 intersection of real part of s greater than 0, where x of t Fourier transform, the Laplace transform x of s, ROC or x1 of t, ROC R1, x2 of t, x1 of ROC R2 respectively. Initial value theorem, f of 0 equal to limit s tends to infinite s into f of s. Final value theorem, f of infinite equal to limit s tends to 0 s into f of s. Initial value theorem is applicable only for Laplace transform, that is the denominator power of function is more than numerator power. Proper Laplace. Final value theorem not applicable if poles are conjugate on imaginary axis or poles lie in the right hand side of the s plane. Laplace transform of elementary function, transform pair signal del of t transform is 1 or is or s u of t 1 by s real part of s greater than 0 minus u of minus t 1 by s real part of s is less than 0 t power n minus 1 by n minus 1 factorial into u of t 1 by s power n real part of s greater than 0 minus t power n minus 1 by n minus 1 factorial u of minus t 1 by s power n real part of s less than 0 e power minus alpha t u of t 1 by s plus alpha real part of s greater than minus alpha e power minus alpha t u of minus t 1 by s plus alpha real part of s less than minus alpha t power n minus 1 by n minus 1 factorial into e power minus alpha t u of t 1 by s plus alpha whole power n real part of s greater than minus alpha t power n minus 1 by n minus 1 factorial e power minus alpha t u of minus t 1 by s plus alpha whole power n real part of s less than minus alpha del of t minus t e power minus st all s cos omega naught t u of t s by s square plus omega naught square real part of s greater than 0 sin omega naught t u of t omega naught by s square plus omega naught square real part of s greater than 0 e power minus alpha t cos omega naught t u of t s plus alpha by s plus alpha whole square plus omega naught square real part of s greater than minus alpha e power minus alpha t sin omega naught t u of t omega naught by s plus alpha square plus omega naught square real part of s greater than minus alpha un of t equal to d power n del of t by dt power n s power n for all s. Characterization of LTI systems using Laplace transform causality. ROC associated with the system function for causal system is a right half plane. For a system with rational transfer function, causality of the system is equivalent to ROC being the right half plane to right half of the rightmost pole. The system is anti-causal if its impulse response h of t is not equal to 0 for t less than 0. An LTI system is stable if and only if the ROC of its system function h of s includes the j omega axis. A causal system with rotational system functions h of s is stable if and only if all the poles of h of s lie in the left half of the s plane, that is, all of the poles have negative real parts. Discrete time Fourier transform. The definition of DTFT: consider a discrete time signal x of t. Its discrete time Fourier transform DTFT is defined as DTFT of x of n equal to x of omega that equal to x of n equal to minus infinity to infinity x of n e power minus j ohms n or omega n, where ohms or omega is the discrete time frequency in radians per second. The transform x of omega is a frequency domain transcription or description of x of n. Thus, x of n and x of omega makes Fourier transform panes as x of n discrete periodic DTFT gives the x of omega periodic continuous, and the inverse DTFT, which maps the frequency domain description x of omega back into time, is given as ADTFT x of omega equal to x of n equal to 1 by 2 pi integration of 2 pi x of omega e power j omega n d omega. Jet transform is a discrete time counterpart of Laplace transform. For a discrete time LTI system with the impulse response h of n, the response y of n of the system to a complex exponential input of the form z power n is y of n, z power n h of z. H of z is the Fourier transform function of the system. Jet transform of a general discrete time signal x of z equals sigma n equal to minus infinity into x of n z power minus z. The range of values of z for which above equation defined given ROC of jet transform used for digital filter design, sample data control and system. ROC is the region of convergence values for which the summation sigma n equal to minus infinity infinity x of n z power minus n converges. Properties of ROC. The ROC of x of z consists of a circle in the z plane centered about the origin. ROC does not contain any poles. It is bounded by the poles. If x of n is a finite duration, then ROC is entire z plane except possibly z equals 0 and or z tends to infinite. If x of n is a right sequence, then if a circle x of modulus of z equal to a is the ROC, then all finite values of z for which modulus of z greater than a will also be in the ROC. If x of n is a left-handed sequence, if circle modulus of z equal to a is the ROC, then all finite values of z for which modulus of z less than a will also be in ROC. If x of n is two-sided and if the circle modulus of z equal to a is the ROC, then the ROC will consist of a ring in the z plane that includes the circle modulus of z equal to a. X of z equal to sigma n equal 0 to infinite x of n z power minus n. Left shift x of n plus 1 equal to z into x of z minus z into x of 0. Right shift x into n of minus x of n minus 1 z transform z inverse of x of z plus x minus 1 x of n minus 2 z transform z power minus 2 x of z plus z power minus 1 x of minus 1 plus x of minus 2. First difference, x of n minus x of minus n minus 1 equal to 1 minus z inverse x of z conjugation x conjugate of n equal to x conjugate of z conjugate. Properties of Z transform: linearity: a into x1 of n plus b into x2 of n, a into x1 of z plus b into x2 of z. ROC is equal to R1 intersection R2. Time shifting: x of n minus n naught z power minus n naught x of z, or scaling a power n x of n x of z by a, scale version of R. Time reversal: x of minus n x of z inverse invert R. Time expansion: xk of n equal to x of r n equal to rk 0, otherwise x of z power k r power 1 by k. Conjugation: x conjugate of n equal to x conjugate of z conjugate, or convolution x1 of n convolved with x2 of n x1 of z x2 of z into x2 of z. R1 intersection R2. First difference, x of n minus x of n minus 1 equal to 1 minus z inverse x of z. R1 intersection of modulus of z greater than 0. Accumulation sigma k equal to minus infinity n x of k to 1 by 1 minus z inverse x of z. R intersection of modulus of z greater than 1. Differentiation n into x of n equal to z into dx of z by dz minus dz into dx of z by dz. R initial value theorem: x of n equal to 0 for n less than 0, x of 0 equal to limit z tends to infinity, x of z. Final value theorem: x of infinity equal to limit z tends to 1, 1 minus z inverse x of z, or x of infinity equal to limit z tends to 1, z minus 1 x of z. Characterization of LTI systems using Z transforms. Causality: a discrete time LTI system is causal if and only if the ROC of its system function is the exterior of a circle including infinity. A discrete time LTI system with rational systems function h of z is causal if and only if geometric degree is greater than geometric degree. Stability: an LTI system is stable if and only if the ROC of its system function h of z includes the unit circle modulus of z equal to 1. A causal LTI system with a rational system functions h of z is stable if and only if all the poles of h of z lie inside the unit circle, that is, they must all have magnitude smaller than 1. Inverse Z transform. As in the case of Laplace transform, there is a formal expression for the inverse Z transform in terms of integration in the Z plane: x of n equal to 1 by 2 pi z circular integral of c x of z into z power n minus 1 dz, where transform of Z transform of del of n equal to 1, or versus all z u of n equal to 1 by 1 minus z inverse modulus of z greater than 1 minus u of minus n minus 1 1 by 1 minus z inverse modulus of z less than 1 del of n minus m z power minus m all z except 0 if m greater than 0, or infinity if m less than 0. Alpha power n u of n 1 by 1 minus alpha z inverse modulus of z greater than modulus of alpha minus alpha power n u of minus n minus 1 1 by 1 minus alpha z inverse modulus of z less than alpha. N into alpha power n u of n means alpha z inverse by 1 minus alpha z inverse whole square modulus of z greater than modulus alpha minus n alpha power n u of minus n minus 1 means alpha z inverse by 1 minus alpha z inverse whole square, but modulus of z less than modulus of alpha. Cos of omega naught n u of n equal to 1 minus cos omega naught into z inverse 1 separate minus of cos omega naught into z power minus 1 whole by 1 minus of separate 2 cos omega naught z inverse plus z power minus 2 modulus of z greater than 1 sin omega naught n u of n sin omega naught z inverse by 1 minus 2 cos omega naught z inverse plus z power minus 2 modulus z greater than 1 a power n cos omega naught n u of n 1 minus a cos omega naught z inverse by 1 minus 2a cos omega naught z inverse plus a square z power minus 2 mod z greater than a power n sin omega naught n u n a sin omega naught z inverse by 1 minus 2a cos omega naught z inverse plus a square z power minus 2 mod z greater than a. The discrete Fourier transform is basically Fourier transform of sample signal repeated periodically. The number of points in DFT is known as n point DFT. The definition: consider a sampled and periodic signal x of n. Its discrete Fourier transform given as DFT of x of n equal to x of k equal sigma n equal 0 to n minus 1 x of n e power minus j 2 pi k by capital N into small n. The signal x of n and x of k makes DFT pair as x of n discrete periodic dft, x of k discrete periodic, and the inverse dft can be obtained as x of n equal to 1 by n sigma k equal 0 to n minus 1 x of k e power j 2 pi k by capital N into small n, where omega equal to 2 pi by capital N, where n is the period of the signal x of n. If x of n tends to dft of x of k, then linearity a x1 of n beta x2 of n alpha x1 of k beta x2 of k time shifting x of n minus n naught dft equal to e power minus j 2 pi by capital N k n naught x of k. Shift in k domain x of n e power j 2 pi by capital N k naught n dft x of k minus k naught conjugate symmetry x conjugate of n. Linear convolution x1 of n convolution with x2 of n with period n1 plus n2 minus 1. Periodic convolution x1 of n convolve with x2 of n 1 by capital N x1 of k into x2 of k into convolution. Parseval's relation E equals sigma n equals 0 to n minus 1 x of n square equal to 1 by n sigma k equals 0 to n minus 1 x of k square. The n point dft is given as x of k equals sigma n equals 0 to n minus 1 x of n e power minus j 2 pi by capital N whole power kn. To compute 1 sample dft, it is required n multiplications and n minus 1 additions. To compute n point dft, it is required n square multiplications and n into n minus 1 additions. In general, we can say as n increases, this computation becomes time consuming even for high speed computer. Number of additions equal to n log n base 2, number of multiplication n by 2 log n base 2. Digital filter is a system that performs mathematical operations on a sampled discrete time signal to reduce or enhance certain parameters of the signal. There are two types: finite impulse response filter. The impulse response is of finite duration. The difference equation is given by y of n equal to sigma I equal to 0 to n bi x of n minus I. X of n, y of n, input and output respectively, n filter order, bi value of impulse response at ith instant. Properties: no feedback is required. They are inherently stable. Given the equation y of n equals sigma equals 0 to n bi x of n minus I. They can be easily designed to be linear phase by making the coefficient sequence symmetric. Computationally complex moving average filter y of n equal to b naught x of n plus b1 x1 xn of x minus 1 plus b2 x of n minus 2. The infinite impulse response of IAR filters continues indefinitely. The difference equation is given as y of n equal to 1 by a naught sigma I equal 0 to p bi x of n minus I minus sigma j equal to 1 to q aj y of n minus j. P feed forward filter order, q feed forward filter order feedback. P means feed forward filter order, q feedback filter order, bi means feed forward filter coefficients, ai means feedback filter coefficients. Properties: feedback is required. Stability depends on the filter coefficients. They are preferred over FIR filters for their efficiency in implementation. Y of n equal to y of n minus 1 plus x of n. Basic structures for IAR systems. Casual IAR systems are characterized by the constant coefficients difference equation or equivalently by the real rational transfer function of equation. From these equations, it can be seen that the realization of infinite duration impulse response system involves a recursive computations algorithm. In this section, the most important filter structure, namely direct forms 1 and 2, cascade and parallel relations for IAR systems, are discussed. H of z equal to y of z by x of z equal to sigma k equal 0 to m bk z power minus k by sigma k equal to 1 to n ak z power minus k. Basic structures for FIR systems. The system function of the FIR system, whose realization take the form of a non-recursive computational algorithm, may be written as x of z equal to sigma n equal to 0 to m minus 1 h of n z power minus n. That is the impulse response if m is m samples in duration. The h of z is a polynomial in z inverse of degree m minus 1. Thus h of z has m minus 1 poles at z equals 0 and m minus 1 zeros that can be everywhere in the finite z plane. FIR filters are often preferred in many applications. They provide an exact linear phase over the whole frequency range, and they are always Bibos stable, independent of the filter coefficients. Two simple realization methods for FIR filters, which direct form and cascade form. IAR filters, length of h of n is infinite. FIR filter, length of h of n is finite. IAR filter design of IAR filter may become unstable. FAR filter it is always stable. IAR filter point its design involves less number of delay elements, adders, multipliers. That is design is simple. Whereas FAR filters design involves more number of delay elements, adders, multipliers. Design is complicated. IAR filters less memory is required. FAR filters more number of memory is required. In IAR filters, it cannot be designed with linear phase. In FAR filters, it can be designed with linear phase. In IAR filter, we have delay or phase distortion in the output. In FAR filter, linear phase. FAR filter will not have delay or phase distortion. In IAR filter, faster response. In FAR filter, slower response. IAR filter is recursive. FAR filter is non-recursive. The realization of linear phase FAR systems, if the impulse response is symmetric about its origin, linear phase results. If all zero filters has a linear phase response, a special non-recursive structure that reduces the number of multiplications by approximately one half can be implemented. The impulse response for a casual filter begins at 0 and ends at m-1. As discussed, a linear phase FAR filter to length m is characterized by h of n equals h of m minus 1 minus m. H of m minus 1 minus n. The symmetric property of linear phase FAR filter is used to reduce the multipliers required in this realization. Comparison of designing methods. Three methods of FAR filter design, that is Windows frequency sampling and Chebyshev methods. Advantages of Windows design method. Simple method for design. Various window functions can be used depending upon the application. Disadvantages of window design method. Lack of precise control of the critical frequencies omega p and omega s. Omega p and omega s depend upon type of window and filter length m. Advantages of frequency sampling method. Simple method of design, simple realization, frequency domain, better control over omega p and omega s. Disadvantages of frequency sampling method. This method is suitable only for frequency domain realization. Miscellaneous unit doublet function. The derivation of a unit impulse function is called as unit doublet. Properties: del dash of t equal to d del of t by d of t. Del dash of at equal to 1 by a modulus of a del dash of t. All even derivatives of del of t are even functions of time, while odd derivatives are odd functions. If f of t is any function, then f of t del dash of t minus a equal to f of a del dash of t minus a minus of f dash of a del of t minus a. Integration of minus infinity to infinity f of t del dash of t minus a equal to minus d by dt of f of t equal to a. Response of LTA system to a sinusoidal input. Any LTA system does not affect the frequency of input signal. Only amplitude and phase changes takes place. A cos omega t plus theta h of t or h of omega equal to a h of omega naught cos of omega t plus theta plus angle of h of omega naught, where a h of omega naught magnitude of response at omega equal omega naught, angle of h of omega equal phase response at omega equal omega naught. Phase delay is the delay offered to the phase of the input consisting of single frequency. Phase delay equal to minus phi of omega by omega. Group delay is the delay offered to phase of input consisting of multiple frequencies. Group delay equal to minus d phi of omega by d omega. For distortionless LTA systems, both group delay and phase delay are constant and are equal. Any band-limited signal x of t is uniquely determined by its samples. If the sampling frequency omega s greater than twice the maximum frequency omega m present in the signal, this is sampling theorem. Omega s greater than 2 omega m. There are two types of sampling: ideal and instantaneous sampling, zero pulse width, practical sampling, non-zero pulse width. First one, natural sampling, flat top sampling. The reconstruction of a continuous time signal from the samples can be done using a low-pass filter or a band-pass filter. The spectrum components of omega L are 2 omega h. The sampling frequency omega s is given by omega s greater than or equal to 2 omega h by k, where k equal to omega h by omega h minus omega L. K must be integer for any integer and satisfy 1 less than or equal to n less than or equal to omega h by omega h minus omega L. Floor function. It is called as floor function. Correlation is a measure of relation between two signals. For two signals, f of t and g of t, correlation is defined as integration of minus infinity to infinity f of t g of t minus tau d tau equal to f of t convolved with g of minus tau at t equal to tau. Autocorrelation function is a special case where both the signals are same. For energy signals, alpha for tau equal to integration of minus infinity to infinity f of t minus tau d tau equal to f of t circle convolution of f of minus t at t equal to tau. For power signals, alpha of tau equal to limit extension to infinite 1 by t integration of minus infinity to infinity x of f of t minus tau d tau. Properties of autocorrelation function: alpha of tau is even, alpha of tau equal to alpha of minus tau, alpha of 0 greater than alpha of tau. For energy signals, energy equal to alpha of 0. For power signals, power equal to alpha of 0. For energy signals, Fourier transform of alpha of tau gives energy spectral density, that is alpha of tau equal to f of omega into f conjugate of omega. ESD of F. For power signals, Fourier transform of RF of tau gives power spectral density. RF of tau equal to limit t tends to infinity ft of omega whole square by t, power spectral density of function. The autocorrelation function of a binary rectangular random pulses train x of t equals sigma minus infinity into a n pt minus nt plus t naught, where a and n are independent variables with values plus or minus 1 equal probability t naught time offset uniformly distributed between plus or minus t by 2, and p of t is pulse width amplitude a, and width t is given by rxs of tau equal to a square into 1 minus of modulus of tau by t, modulus of tau less than or equal to t. Pre-enveloped complex envelope, let x of t be a real band pass signal with Fourier transform as x of omega, then x of p is its pre-envelope and x of t is its complex envelope. Pre-envelope xp of t equal to x of t plus j into x h of t, and xp of omega equal to x of omega u of omega, where x and h of t equal to Hilbert transform of x of t, xp of omega Fourier transform of xp of t u of omega unit step signal. Complex envelope x of t equal to xp of t e power minus j omega ct, xa of t plus j xq of t, x of t equal to real part of xp of t equal to xa of t cos omega ct minus xq of t sin omega ct, where xa of t xq of t is in phase and quadrants components respectively. Omega is central frequency of carrier. Complex envelope is a low pass signal. Pre-envelope is a band pass signal. Complex envelope and pre-envelope are frequency shifted versions of each other.